welcome back to our new topic, which is isomerism. So this is the part 3 of the isomerism, where we will learn and also discuss about optical isomers. So this is what we have learned in part 1 and also part 2. We have learned about the constitutional or structural isomers and also stereoisomers, where in the part 2 we have discussed about geometric isomers or cis-trans isomers. So in this part we will learn about the optical isomers, or known as enantiomers, where actually they have non-superimposable mirror images. So what is an optical isomer or enantiomers? They are actually stereoisomers of molecules or ions that are non-identical mirror images to each other. So objects that have handedness are said to be chiral or non-superimposable, means like non-superimposable, tidak bertindan ataupun tidak bertindan. And then object that lack handedness are said to be achiral or superimposable. So in these optical isomers, okay, we have two terms that you need to remember: chiral and also achiral. Then an object or compound is achiral if it has a symmetry plane cutting through the middle. And then this is what we call handedness. So if you see your hand here, right, and then you put this hand to this hand, this is where we have the non-superimposable, right? Not like this. It's supposed to be like this. So this is where we have the non-superimposable or chiral. So the definition of chiral is actually usually the carbon chiral, where actually the carbon is bonded to 4 or more different types of ligand. As you can see from here, this is a chiral carbon, and it has 4 different types of ligands bonded to the carbon. Like for example here, carboxylic acid, the alkyl group, the NH2 amine, and also hydrogen. So the optical isomers are non-superimposable mirror images. So in this case, we have cis and also trans, where cis, you know that from this example, cis, it has two similar or two identical ligand at the same site here. While for the trans, we have opposite ligands or opposite sides of ligand, for example here and also here. So when you draw the what we call mirror images, you need to reflect back this kind of compounds. So this is the actual, right? Then this is the actual compound, and this is the mirror image. And then this is the actual compound, and this is the mirror image. So this is the cis of cobalt compound, cobalt complex, and this is trans of the cobalt complex. And as here, this cobalt compound here, cis, is actually optical isomers and also chiral, while for the trans, it is actually a not optical isomer and also achiral. Why? Okay, let's say this is A1, this is A2. Alright. Let's say you draw A to the A1, the A2 to the A1. So what happened here? Let me draw back the compound. So this is the Cl, this is the Cl, and then we have here, this is the En. It is supposed to draw like this, the En, and then we have the mirror image. Let me change the color first, blue, the mirror image of A2 here. So what happened here, you will see this is where you have the first EN, and then the second EN, and then you have the CL here and also CL here. This is what we call chiral or optical isomers, because they are both non-superimposable images. But if you have the trans, okay, for example, let me change my color pen. Okay, so trans, let's say this is the B1, this is the B2. I draw to you the B1 first, and then we have CL here and CL here, and then so this is at the same plane, similar to the B1. So what would you get? This is where you have the CL and also the CL and also the EN and also this EN. This is what we call not optical isomers, because they are super impossible to each other. While for this one we call as non-super impossible, tidak bertindih, while this one is bertindih. And then other than that, I have a sample problem here at 23.4. So the problem here is you need to draw all stereoisomers for each of the following and state the type of isomerism. So first thing is, for the first step here, you need to draw first and determine what kind of isomerism that these two compounds have. So for the first one, it is obviously to have trans and also cis, because we have only 4 ligands, and this is a square planar compound, square planar. While for the B, we have the chromium with 3 ethylene diamine. So this is actually the tris ethylene diamine chromium 3, where the EN is the this is the formula for EN. So just to inform you guys, in order for you to draw the EN, you can draw it like this. Okay, let's say this is the metal, and here you need to put the EN. Okay, so it means that it's actually a bidentate ligand where metal connected to the first nitrogen and second nitrogen. So this is actually nitrogen number 1 and this is nitrogen number 2, because you can see here this first and also 2 second. So this is a ligand, only one ligand with 2 donor atoms, so bidentate. And then this is answer for A, and these are both geometric isomers and they are not optical isomers, because they are super impossible to the mirror image, means that they are bertindih, okay, superimpose. And then what about B? First thing is you need to draw, and then you need to identify the isomers that for this compound has. Okay, so here this is the chromium 3, and then you need to draw the mirror image, and then you need to start overlap this. For example, this is A1 and the second one is the A2. So you need to overlap either one, whether you want to overlap A1 to A2, A2 or to A1. So for example here, let's say I overlap A2 to A1. So this is the new N, and then I have new here, and then I have new here, En. Okay, so this is where you have the what we call optical isomers. So other than like this, En, ethylene-diamine, this is the metal, you can draw the ethylene-diamine like this, N. Okay, so these are correct, and don't draw this and then write down as En. This is totally incorrect, because you know that ethylene-diamine is a bidentate, so you need to show the two donor atoms. So if you rotate this compound, this chromium, you still get what we call optical isomers, and they are non-superimposable to each other, so it can be considered as optical isomers. So other than that, we have example for the cobalt, cis and also trans. Yeah, here we have cis and also trans, so you need to be able to identify, and you need to be able to draw. So please, at home, please try to do a few exercises other than tutorial, and also exercises that I have given to you during our virtual class. Okay, and then we have cis and also trans. And as you can see, cis are actually chiral, so cis is considered as non-superimposable or optical isomers, while for the trans, it's actually achiral, or what we call superimposable, and this is not trans, usually not be considered as optical isomers. And then other than that, I have this is also similar example in sample problem. We have here cobalt 3 ethylene-diamine cobalt 3, where it actually exists in two isomeric forms that are mirror image to each other, so this can be considered as optical isomer, because they are because they are non-superimposable. Yeah, this is another example, similar example here, where you can see the right-handed and also left-handed imposed to each other, so it will form like this, handedness. And then because we have bidentate ligands, and then here another one, we have also cobalt 3 complex ions, where it actually achiral, because as you here, because why? Because we have here 6 amines. So if you draw the mirror image of this compound, you will get the same shape or symmetry plane of this compound. And then how to identify the enantiomers, or how to determine the formation or how to characterize the enantiomers. So enantiomers have identical properties, they have similar properties except for their reaction with other chiral substances and their effect on what we call plane polarized light. So in these enantiomers are usually, we call it as optical isomers. Their effect on plane polarized light can be measured with what we call polarimeter. This is an instrument that you want to use if you have enantiomers, in order to identify the properties. Okay guys, so this is actually how to identify the enantiomers using polarimeter. So in this polarimeter, this is a model of polarimeter, where you have the light source, and then you have the fixed polarizer, and also polarimeter tube, where actually this is where you need to put your sample in a solution, and then after the polarimeter tube, we have the plane of polarization or analyzer, and this is the result that you get, whether it is positive or negative. Yeah, positive and also negative. So in order for you to get the plane polarized light, okay, it's actually you need to obtain by passing the ordinary light here, the light source. You need to pass the ordinary light through a polarizing filter. So this is the polarizing filter, and then in this polarimeter, this is where the plane polarized light is passed through. A chiral solution where you have your own sample here, and the polarization plane here will give you results, and also using the analyzing filter. And here, as I mentioned before, you will get positive and also negative results. Let's say you get the positive or the plane rotates to the right, positive. This is what we call dextro-rotary, to the positive. And if the plane rotates to the left, it will. This is what we call levo-rotary. And then I have 2 exercises for you to do at home, and we will discuss this one later during our meeting. So this is first exercise and also the second exercise. And yeah, I think that's all for part 3 for isomerism. Hope to see you again in next topic. So please don't forget to like, comment and subscribe. See you guys. Bye.